AP Calculus. Today we're going to start in the actual AP Calculus textbook. So I would like you to grab it and have it handy. And you're going to turn to section 1.1, and it's on a preview of calculus. Um, it starts on page 4142. So you'll need to grab that. And then I wanted to talk to you a little bit about the author of the book is Larson and Edwards. And so when we're looking at the sections, often in AP Calculus, I have my students read the sections. Um, this is an AP course, so the textbook is written more on a college level. So it will take some time. I know most of you probably have already had an AP course, but I did want you to get familiarized with like the terminology they use. It's very technical, and you're going to have to kind of get used to it, especially before college. The more experience you have with it, the better, easier it's going to be later. So one thing I would like you to do for an assignment, I can't post this on Canvas, but I would like you to read through the entire section 1.1. Some of the things obviously I'm going to be touching on in the video, but I need you to start, it's like a learning curve, trying to understand how the textbook is written, and again, trying to get used to the technical language they use. I would like you to, in your notebook, write down the learning targets. Always do that. First one is I can understand and identify what calculus is and how it actually compares to pre-calculus. Learning target 2, I can understand that the tangent line problem is basic to calculus. 3, I can understand that the area problem is also basic to calculus. So we're going to look at a comparison between calculus and pre-calculus. And a little note on this, when I mention, and the textbook mentions pre-calculus, that does not refer to the class you took last year. Pre-calculus means any math class you took before calculus. So Algebra 1, Algebra 2, Geometry, and pre-calc. Second, we're going to look at the tangent line problem and how it is a very basic concept to calculus. And then area, I'll just touch on, and we'll learn a lot more about these two throughout the course of the year. Okay, some background information on calculus. Calculus is mathematics of change. It takes regular rules of math and it applies them to changing problems. There are two founders of calculus, and their names are Leibniz and Newton. And this one I'm sure you've heard of, Isaac Newton, before, but both of them are credited for being founders of calculus. The difference between regular math, again pre-cal is how this textbook will describe it, and calculus is curves. Like that's the difference. Here is a real-world example of calculus. When you read this section, you will see this show up. I'm giving you kind of a preview. If you're pushing a crate up a hill, like looking at it, if you're standing here, you have this crate and your job is to push it all the way up to the top of this hill. When the incline is straight and you're going to be like, let's say you're going to move at a constant speed, you're not going to stop and rest, but you're going to go constant speed till you accomplish your goal of reaching to the top. This is a straight line. There's no curve to it. So this would be an example of what they call a pre-calculus type problem. However, it changes if the hill isn't straight, like straight, diagonal. If it has a little curve to it, let's say you're here, you have a crate, you start pushing the crate or like up the incline, and the steepness changes, like right there, and then it's a little bit flat, and then it rises and a little bit flat and rises even more. And so because there's so many different things going on there and the steepness is changing no matter which point you're looking at, you have to exert a little bit different amounts of energy. And so this is a calculus problem. And that's why it says it's a math of change, because the effort I put forth here is going to be different than here and here, for example. Another example, just to make sure you understand the comment I'm making about the difference in calculus and other math. An example 2 would be like if I had a flat roof and I was trying to calculate the area. Well, if it's flat, then I would just need to know what the dimensions were here. I'm just going to call that length. And the dimensions here, which would be the width. Okay, and so I would just multiply those two numbers together. That's really a geometry problem. But if it's a flat surface, two-dimensional, then again, that's why it's called pre-calc. Well, if I'm calculating the area of a complex like a dome shape, then this steepness is different than this one, and this one, and this point, and so on. And so this would require me to do a little bit more mathematical formula to figure out like the actual area for that. So calculus basically works because what your job is going to be doing, like one of your jobs this year, is learning how you can take curves and zoom in on like one location at a time. And if you zoom in close enough to the curve, the sections are going to become straight. And then if we can do that, then we're allowed to use regular algebra rules and geometry rules. So even though we know this isn't straight, we'll take like one specific location and zoom in on that location as close as we can get, and kind of think about it as straight, use regular algebra rules, and the zooming in process is achieved through what's called a limit. And a limit is one of the big 3 ideas in calculus. So there's like 3 major concepts in calculus that you'll learn this year and in college. And those big ideas, number 1 is on limits. That's what we'll study first. And 2 is on a derivatives. We'll learn a lot about that. And then hopefully we'll get enough time this year to look at some integrals as well. So those are the 3 big ideas in calculus. Super, super important. Okay, so next, what we're going to do is take a look at what's called the tangent line problem. Just to review, tangent here is actually the definition like the geometry definition, and not like tangent graphing that we just finished in the last unit. So I'm not talking about a trig graph here, or even like for secant as well. I'm talking geometry. So it may have been a while since you've had these words, but tangent line is a line that intersects the graph at one location. And then when you hear me say secant line, I'm wanting you to draw a line that's going to intersect whatever graph they give you in 2 places. So tangent is 1 and secant is 2. And so what I'm going to have you do now is copy everything down you see on the screen. When you're graphing, I want you to graph like just a family, like a parent graph of y equals x squared, the quadratic family. You can see mine's in blue. And then I would like you to also draw in, like, and you may want to use different colors here, but the red line is the tangent line. I'm going to call it line T. and then the green line is on line S, secant, and I want you to try your best. You can use a straight edge as well. Try your best to get the tangent line to cross the parabola at like one location. Actually, make sure try to make it cross there at 1, 1. That's according to the directions. And then on the secant, make the green line, the secant line, cross at 1, 1. So the same location, but also at 2, 4. And we're going to look at, like, what is the slope of the tangent line T? How steep is the parabola at 1, 1? So here's our main question. What's the slope of line T in red, and how steep is the parabola at that specific location? And again, just kind of throwing it back to the things I've already said, the blue, the parabola is a curve. And then obviously the tangent and secant are lines, they're linear. So what we're basically trying to do is kind of introduce you to the idea of limit and how we have to take a curve and focus on like one single point at a time and zoom in close enough to kind of make it look like it's straight there even though it's not, and find the slope of the lines S and T, because if we can do that, then that's going to help us estimate the slope of the parabola at 1, 1. And so let's start with S first, because it is a line that I can clearly find 2 points. When I have 2 points on a line, I can just use the slope that we're used to from algebra 1 and 2, and that's just y minus y over x minus x. So when I'm looking at 1, 1 and 2, 4, then I'm going to, this is x1, y1, x2, or y2, but we're just going to subtract, and we're just going to get 4 minus 1 divided by 2 minus 1, and the answer is 3. So the slope of the green line can be found using algebra. It's a little different when you look at line T though. Line T, I only have one location right now, and it's at 1, 1. And where I've just kind of sketched this in, I really don't know. I would have to kind of estimate where other points are. But to be accurate on finding the slope of line T, I actually have to get a little bit more information. And so the limit process allows you to kind of slide the point 2, 4, which is right here, closer, kind of on the secant line, down closer to point 1, 1, that's on the tangent line, to help you find a good answer for the slope. So let me say that again. It's basically you're taking a line that you know 2 points for, you're finding its slope like you have been used to in the past using the slope formula from algebra. But then when you're given a line and you only know one location on it, you're going to take one of the points on the secant line and basically kind of imagine sliding that point down. The closer you can get to 1, 1, then kind of zooming in on it, that location will give you the slope for the tangent line. It's just a good approximation for that. So if we can figure out what the slope is at line T at 1, 1, it's also going to help us find the slope of the parabola at 1, 1. Okay, so finding the slope of the tangent line is the same answer as finding the steepness of the curve at that point. And so what I've done is just kind of recreated a similar picture, same kind of deal. My parabola is in blue. I have my tangent line in red. My secant line is in green. And at point P, the location of that, we're going to just be general right now and just call it C, comma, F of C. I could have called it X and F of X. I just used those letters. So let's say C is your X and F of C is your Y. And then go to point Q on your graph. It's in green. And it is on the secant line. And so basically what I've done, and again this would be a little bit easier in person, but what I've done is I've taken the red, the point P, and I have gone right, and I have gone up, right and up. And so the amount that I go right is illustrated here, and I've used, that's supposed to be a triangle there, delta, it's called delta X, and then the distance from here up to Q is F of C plus delta X. Alright, so all that means is delta X is, it just means change in X, the change in X. So if I start here, I have to, and this is C, okay, this is your X, C, I have to add something to it to get to Q. And so that's what this stands for. And then on the Q part, on the Y part, you're going to look at it in terms of, well, if F of C is the Y, you're going to add delta X to it, so it's going to go this distance. And so if these are my two locations, then I need to find the slope of PQ by doing y minus y over x minus x. And this is called the difference quotient. When you read through your section, hopefully you'll understand a little bit better, but the f of c plus delta x minus f of c is coming from me taking this y, this is my second y, subtracting my first y from it, and then c plus delta x is my second x, and I'm subtracting c from it. And so this, again, is called your difference quotient. It's really the same thing as y minus y over x minus x. Okay, so look back at your picture. As point Q, which is on the secant line, approaches point P, the secant line is approaching the tangent line. And so when that happens, the slope of the secant line is approaching the slope of the tangent line. So that basically means the slope of the tangent, slope of the line T, can be thought of as equal to the limit of the slope of the secant. As point Q approaches point P, the secant line approaches the tangent line. So imagine me sliding it down, kind of taking this line and kind of moving it, kind of slanting it towards it. And the slope of the secant line approaches the slope of the tangent line. So that means the slope of the tangent line, the slope of the red line, is going to be equal to the limit of the slope of the secant. And I understand you don't know anything probably or very little about limits. That this is kind of trying to get your minds thinking in that direction, and then this will make more sense when you get there. Okay, and the third concept in this section is called the area problem, and this is just very, very brief. To find the area under a region bounded by a curve, you're going to use limits, and this, again, is something we're going to be talking about in the next section. But you're going to approximate how many rectangles you can actually fit underneath the curve. So if you look at my picture, I just drew a random red curve. I can call it f of x. And the area under that curve, so the space highlighted in yellow, can be found by an approximation, actually, by figuring out how many rectangles you can fit underneath that curve. Now technically, I didn't do a great job of drawing this. It would have been better if these rectangles had actually kind of touched the red curve at some point. And so I tried. This one's off a little bit too, but hopefully you get the idea. The wording means all the rectangles have to be underneath. And so as the number of rectangles increase, like if I can figure out a way to make the widths smaller and fit more rectangles, then the approximation of the area of the curve becomes more accurate. In other words, the more rectangles I can draw, and find the area of each one of these, if I could add like all of it together, I would get a pretty good answer for how much area is in this yellow space. Okay, and then I just made kind of quick comment. There's a lot more on this later. But when you hear me say area, I need you to think about it in terms of like space underneath a curve and how many rectangles you can fit underneath. And then when you hear the tangent line problem, that's trying to get your minds thinking about limits. Okay, so this is connection to a limit in calculus. Which is one of the three big ideas. And then let me go back over here, since I didn't say this a second ago, and I should have. Area is all connected to integrals. And that will be like probably the last content that we cover this year, based on time. So section 1 in your textbook just kind of gives you a really small preview of 2 of the 3 big ideas in calculus. Alright, so again, please read through the section. Read it, reread it. You might have to read it twice. Try to get yourself starting in the motion of understanding the wording they use. And then your assignment is going to come from page 47, the first section, and I will send that to you on Canvas. Okay, so I did the best I could with doing this online, but when we get back in person next week, we can go over anything that you have questions on. Okay, so give it your best try.